All right, so moving on to section 2 of this regression stuff, we have fitting a line by the least square regression is what we're looking at. So there's many different processes that you could use to find the line of best fit for a regression, and we're going to be looking at the one that's most commonly used, which is your least square regression. Okay, and so let's start off with this. So what would be best? So when looking at a scatter plot and you're trying to find the line of best fit, what should be true about the residuals? So remember we talked about residuals, that was the distance between your line of best fit and each data point. So which would you want if you were drawing a scatter plot? Which would you want? Would you want all the residuals to be equal, so all of them to be the same? Would you want all the residuals to be as large as possible or as small as possible? I hope you picked C because it should all be small. The smaller it is, the better the fit is. So if all your residuals could be 0, that would be perfect. The problem is that when we're doing a linear line with a scatter plot, it's almost impossible for them to be 0, okay, because one point can throw it off. But what we're looking for is we're looking for the smallest residuals possible. Okay, so these are two different methods that you could use for finding the overall residual that's going to be the smallest. One is just taking the absolute value of each point based on your line. So the absolute value of one point minus the residual, or the y at that point, plus the absolute value, yada, yada, yada. And you do it for all the points, and you find the sum of them. Okay, that's one way of doing it. Another way of doing it, which is the way that we're going to end up using, is called the least square method, which is you take the difference of each point and then you square them. Okay, and you're probably sitting there, well, why would I want to square it when I can just subtract it? Well, there are 3 reasons, which we're going to say in the next slide. But these are your 2 different ones. This is the one that we're going to be using more often, is that bottom one, which is the least square method, which is finding the difference between each one, squaring them, and then finding the sum all the way across. Okay, you don't have to do this by hand. Your calculator does all this. Okay, so why do we use the least square method? There's 3 reasons. Number 1, it's the most commonly used one in statistics. Your calculators use the least square method for this. Okay, and the second reason is why your calculator uses it. It's a lot easier to do it by hand and on the calculator and to do a computer program to set up a least square method than it is with the absolute value. Because that absolute value part is the tricky part where you need everything turning positive, it's easier to just say, well, just square every number. Because when you square every number, all numbers turn positive. And last and most importantly, that if you have a point that is farther off that line, we want to give it more weight. So if you think about this, if I have a residual that is 3 units off of the line, okay? If I just did my normal one, that would just be 3. If I did my squared, that would end up being 9. So it's larger, okay, because I square 3. And then compare it, if I had a unit that was, or a point that was only 2 units off, 2 and 3 don't seem very different. They're fairly close. But if I square it, it's 4. So now if I compare 4 and 9, that's an even larger difference. So things that are farther away from that line get exaggerated. And that helps with this making a better line, that those points that are farther away can affect it a little bit more. Okay, so they're very minor differences here. Okay, so it's a minor difference between the two. One's a dotted line, one's a solid line. The dotted line is the normal, or that first equation where you just take the absolute value. The second one is the least squared. So that solid line is the least squared. And as you see, there's a slight difference. These points are kind of pulling that line up a little bit more than the first one. So there's a slight difference, but we want to only use that least square regression. And again, your calculator can do all this. Okay. There are some requirements for this. Requirements for this is that it needs to be linearity, nearly normal residuals, constant variability, and avoid time series. Okay, and we're going to look at examples of each one of these. So first one is linearity. So the data must have a linear trend. Okay, if it doesn't, we should probably use a different regression. So if you look at this example to the right, you see that it is more curved. And you see the residual, you see that the data is curved. So that tells us that it's not linear. So this would be one that we probably wouldn't want to use a linear line for because we have some sort of bump in it, we have a curve in it, and it doesn't really fit. So that's why we need linearity. The data needs to look like it's a linear trend, not some sort of curve or a peak and a valley. Okay. All right, next up is that we need nearly normal residuals. So all the residuals should be fairly spread out evenly. Okay, so like if we just look here at the end of this would be perfect for ours. Okay, but the problem is that we have these two outliers, and we're going to talk about specifically what these outliers are and what they do. But they should be, this is what you want it to look like. You want it to look like that. All the points are kind of together, they're bunched together, and that line is easily formed. We don't want outliers that are really just throwing things off. That's way out of tune. We want to identify what those outliers are and why. Okay, so we shouldn't have outliers present. Now, it's almost impossible you'll always have outliers present in any sort of data. Constant variability. So the constant variability basically means that whatever the distance is between all the points at the beginning of the function should be about the same at the end of the function. So as you move along the x-axis, the residuals shouldn't converge or diverge in either direction. So you see here with this graph, you see that the points start spreading out, start fanning out. And the residual, you can see it even more. You see that they start moving away from each other. So that tells us that, yes, at the beginning we could use linear, but then after that, something's happening. Something's happening with that data, and it's not staying constantly linear. It's going to be changing in some way. And we should try to figure out what that is, but it might not be linear. So if it fans out, or if it goes the reverse, so if you look at this going from right to left and you see it all converging onto one, that also isn't a constant variability. So we want it even all the way across. We don't want it to fan out or shrink down, or do both, kind of bubble in some way or another. So we want to avoid those. Okay, last one is a time series. So a time series basically means that the data was collected in some sort of sequence, and you can see some sort of pattern. Okay, so you can see here that there's some sort of pattern that was formed that was built in the collection of this data. Okay, so we want to avoid any type of time series. So those are the reasons. Those are what we want to do when we're looking for our regression. We want to avoid those. Some of them can't be avoided. Others could be. Okay, so if we look back at this this example of how much money families get based on how much they earn, gift aid from a university, we want to know would a linear model work. So the first thing is there any obvious outliers that we have? No, there's not really any. They're all kind of close to this line. There's nothing that's way out there. And again, we're talking about outliers would be like something like way down here or way up here. They're kind of exaggerated. These points here we would still say are fairly close. They wouldn't be outliers in any way. Is there a time series? Doesn't look like it. Doesn't look like there's some sort of pattern as it moves across, and the data looks fairly consistent. So since the data looks fairly consistent, we would say that this probably, yes, we could use a least square regression on this, and it would work out fairly well. Okay. All right, so finding the least square regression. So the least square regression, which again is our equation, y hat is equal to beta 0 plus beta 1x. Okay, to find the slope, what we're going to do, which is your b1, you take your correlation coefficient, or that r, and then you multiply it by the standard deviation of the response and the explanatory variables. So you take the division of the y over the x, just like what we do with slope. So the slope is the change in y over the change in x, but you're taking the standard deviations of your response and your explanatory variables, your y and x. Do that division, then multiply it by whatever the correlation coefficient is. Okay, so multiply it by the correlation coefficient, and that's going to tell you if it's positive or negative based on that. Okay. Again, all this stuff is calculated usually through a calculator. This is going to be more if you're given the data. If you're given sy, sx, r, x bar, y bar, all those. If you're given all this information, this is how you can find it. Okay? But if you're given raw data, use a calculator. It's going to be able to do all this for you, and you don't have to do it by hand. Okay, so this would be an example where you have to do it by hand because the data is given to you, x bar, y bar, yada, yada, yada. So we have all this information and we want to look back at this graph. Here's our standard deviation, there's our means, there's our R, okay, and we want to find our slope. So take a second and find the slope of this linear regression. All right, so using the slope formula that we just did, which was our beta 1, we would go 0.499 times 5.46 over 63.2, and so we get our beta 1 as negative 0.0431. That would be the slope of this line. So this line is decreasing by 0.0431 every increase of x. Okay, so that's what we would have. So based on this data, we're able to use that. Okay. Now, once we have that, once we know our slope, now we just have to find our b sub 0. And our b sub 0, what we can use is that we can use our mean values for those. Okay, we don't want to use an actual data point because we don't know if it crosses through that point. So we want to take the average numbers of our x and our y because it should cross through that point, the average. So that's why we use x bar and y bar. So x bar, y bar is this equation, or is plugged in here. Y bar was 19.94, x bar was 101.8. So now take a second, use some basic algebra skills, find b sub 0. Right. So now b sub 0, we end up getting as 24.3. Okay. So now it's 24.3. Now we have our entire equation as y hat is equal to 24.3 minus 0.0431 x bar. Okay. Or x. X, not x bar. No. Just x. Okay. And that would be our number. So now we can use this to help us predict what the amount of money they're going to get. So, quick question: suppose that you have a high school senior and they're looking at Elmhurst College, which is where the data is from. Would you be able to tell them exactly how much money they would be able to receive in financial aid? So they go, okay, my family makes X amount of money. How much financial aid will I get? Would you be able to tell them with 100% certainty that they would get this much money? And the answer is no, because of the 100% certainty. If you didn't have 100%, if you said you could estimate how much they would have, that would be true. So they say, okay, my family makes this much money, how much financial aid? And you can say, well, you can get around, on average, our students get about this much. Okay, so you can tell them an estimated amount of how much they would have, but you couldn't tell them exactly because there are other things. Okay, they could have other scholarships. You know, you could have a academic scholarship, a sports scholarship, whatever it is to add towards your financial aid package. So you can tell them approximately this is how much they get, but not for sure. Okay, and that's the one thing with regressions we have to remember. These are not the end-all, be-all answers. These are an estimate. This is a prediction of what it is. Okay, so what do the parameters mean? So B1 is our slope, so it's the change in the variable as you increase the x by 1. So if the explanatory is increased by 1 unit, how much does the y change? So in that previous example, every $1,000 more the family makes, the financial package goes down by $43. $43, I believe, $403, something like that. Okay, so the slope tells us how much the y changes as the x increases by 1. Negative means it drops. The y-intercept, or the b sub 0, predicts how much the value would be if the explanatory was 0. So in our previous example with this unit, if a family made no money, okay, so if the family had no income, the person would estimate to receive $24,300 in financial aid. Would be the prediction. Okay. Now they could be more, they could be less, but that's the prediction. Now, one thing that we want to make sure is that sometimes the 0 doesn't make any sense. So if you're talking about like people's heights, nobody's a height of 0. So if you're going like height to weight, and you go, oh, as people get taller, they weigh more, type of stuff. You wouldn't go all the way down to 0 because nobody has a height of 0. Nobody has a weight of 0. So you can go, that makes sense if there is a 0 that could be plugged in. Okay, That's just something you have to watch out for, which is our extrapolation. So extrapolation is basically taking your linear model and taking it out of its bounds. So expanding what it is. And again, if we're looking at, let's say, height and weight, if you have somebody that is, if you're looking at between the heights of 5 foot and 7 foot, you're not going to be, we can predict this and go, somebody that is a kid that's 2 feet tall is going to weigh this much, because it might not fit the data, because children grow differently than adults. And some children, I don't know the exact data in front of me, but children could weigh more or less than what their height is predicted. And so we can't expand it beyond what our actual parameters were. Okay. So with this example, so we had dealing with that money. Let's say we had a family that the person made $1 million. Okay, the family made $1 million. How much financial aid should they have? So what we would do is that we'd plug in 1,000 into this X, and we plug 1,000 into this X. What do we get? We end up with negative 18.8. Now, would that make sense that if a family makes $1 million, they have to pay extra for it? In this case, no, because again, it's a gift. It's a financial aid package that they get some money. So the original data didn't go up to $1 million. It only went up to, I think, 200,000, 250,000, maybe $250,000. So we're going and we're basically taking it 4 times as far, and we're expanding it, and that's why it won't work. So whenever you have this regression, you can really only use it to predict within the parameters or the bounds that you have used your data from. So like the previous example from the previous PowerPoint with the, the bush-tailed possum, that was looking at bush-tailed possums whose lengths were between like 70 and 90. So you wouldn't go, well, okay, there's a bush-tailed possum that is, the entire length is only, 30 centimeters. Does his head length work the same? Well, no, because our prediction is that it would be within this bound, not all the way. Okay, so you just have to make sure that you can't extrapolate beyond what is given in this problem. Okay, so you just have to keep it. Okay, yeah. So again, main thing to remember is to use the regression within your own data set to predict within it. Okay, R squared. It describes the strength of the fit. So R squared, or the explained variance, is another way of using to measure the strength of it. And so one way of doing it is taking the standard deviation of the y's squared minus the standard deviation of the residuals squared divided by the standard deviation of the y's squared. Okay, so there's 2 different formulas to get your R squared. Now, you would need both sets of standard deviations. As you see, the x's don't matter because, again, you're just looking at how far away the residuals are. So what's the distance from the line to each one, okay? And so we have those numbers. So both those formulas are the exact same, one's just simplified. Now, again, the easier way of doing it is it's just R squared is equal to R squared. So if you can find the lowercase r, you square it to find the R squared, the capital R squared, okay? It's the same number, it's just being squared, okay? So you just take your lowercase r, you square it to get your uppercase R. And again, your calculator does this, so you don't have to do it by hand unless they give you the numbers to help you find it and everything. So R squared is always going to be between 0 and 1, but it can also be 0 and 1. So if you remember the R, our correlation coefficient, was from -1 to 1. Well, if we square negative numbers, we get positive numbers. So that's why our R squared is always going to be between 0 and 1. It's always going to be positive. It can also be 0 and 1. Obviously, 0 would be doesn't fit at all. 1 would be a perfect fit. And you can kind of think of 0 to 1 as being the percent or the proportion of the y values that explain the regression. So how many of those y's kind of fit that regression fairly well? 1 would be 100%. Every single one fits the regression. 99 would be 99%. So a 1 means that all the y values fit the regression, 100%. 0.5 would mean that 50% of the y's fit the regression. Okay, so it fits it up to a point, but it doesn't fit every single point. Okay. Okay, so if a linear model has a strong negative relationship, correlation of negative 0.97, how much variation in the response is explained by the explanatory variable? So basically it wants the r squared for this. So it wants to know what is the r squared. So you take 0.9, you square it, and you get 0.94. Okay, so your r squared is 94, which would mean what is the percent of the y values that explain the regression? 94%, obviously. Okay, so 94% of the data fits or explains that regression that we have drawn. Okay, so again, it's just taking, when you have your correlation coefficient, you square it to find the variation of the response. Okay. Okay, so if a linear model has an r squared or explained variance of 0.94, what is the correlation coefficient? Okay, so take a second. Okay, so what is the correlation coefficient? It is plus or minus 0.797. Okay, and all you're doing is you're taking the square root of the r squared. Okay, so those relationships, one's being squared, one's being square rooted. Now, one thing we do have to find out is that if we're going from r squared back down to r, we have to put the plus or minus. Because unless the data tells us, we don't know if it's a positive or a negative slope. Okay, so just by looking at an r squared, we're unable to tell if it's a positive or negative slope. So that's why we'd say plus or minus 0.97. Unless we're specifically told that yes, it is a positive slope, or no, it's a negative slope, yada, yada, yada. Okay? Okay, so finding r and r squared on your calculator, here it is. This was on the previous one as well. So here's your step-by-step going through. It tells you what all of them are. And for an 83 and an 84, it's fairly simple. Okay. Okay, so with that, take a second and find the regression and everything using your calculator for this and your r and r squared for this set of data. Okay. All right. So hopefully you got your regression as 5.136 plus 1.056x. Okay, and then with that you can use your r and r squared should have also popped up on those. Okay, but that should have been your equation for it. Okay. All right, categorical predictors with only 2 levels. So assuming, let's say, instead of having a full x where you have from 0 to 10, you only have categories. So in this case, we have Mario Kart being sold on eBay. It can either be bought new or used. And so what you have here is that you're going to try to predict what it is, make a regression line based on the new or used. First thing you want to do is you want to take your categories, you want to give them numbers, kind of ranking them from the larger number is better to the lower number, which is worse. In this case, new is 1, used is 0. Okay, so you have those 2 categories. Now, what you're going to do is you basically find the average of each category. Okay, you find the average of each category, and then you draw your regression line from those. So if you have only 2 categories, you just have to find the average for used. So what was the average price for used, which was $42.87, and the average price for new, which was $53.77. Use those 2 points, write your equation. Okay, that's all you have to do. If you have multiple groups, so let's say you have, new, slightly used, or average, yada, yada, yada. So, if you're buying stuff on Amazon and you've got multiple different categories, you would have multiple points, and then you have to try to fill a line based on those points. Okay, so, but if you're only given 2, you find the average of each category, then graph a line through those. Okay. All right, that's the end of this section, and we'll be moving on to section 3 next.